Hello, I'm Jishnu Mukhoti, and in this video, I'm going to be talking about our paper, Open Vocabulary Semantic Segmentation with Patch-Aligned Contrastive Learning. This work was done with my wonderful collaborators, Sungyu Lin, Omid Pursad, Ray Wang, Ashish Shah, Philip Tor, and Sarnam Lim. Foundation models like CLIP have been trained on massive amounts of data of the order of hundreds of millions of samples in a contrastive setting, and as a result can recognize several concepts in given images. This enables them to perform image recognition or classification tasks, often in a zero-shot manner without any additional requirement of training samples. In this work, we explore if we can leverage this pre-trained knowledge store of concepts and extend it to the task of semantic segmentation, where we require predictions at a pixel rather than at an image level. Specifically, we propose a method to train an alignment between the patch tokens from a vision transformer-based image encoder of CLIP and the CLS token of its text encoder. Learning such alignments helps us in creating a setting where, given an input text, we can identify the region of the image where the corresponding concept can be found. Thereby, this helps us in extending CLIP to zero-shot semantic segmentation without requiring any additional segmentation annotations, masks, or any changes to the CLIP model architecture. Before we dive into open vocabulary semantic segmentation, let's first see what semantic segmentation is. It is a computer vision problem where the goal is to label and predict every pixel. Thus, training a fully supervised model on this problem requires a large amount of fine-grained annotated data. Since collecting such fine-grained annotations is expensive, it limits the number of concepts that a fully supervised semantic segmentation model can learn. Recently, foundation models like CLIP have been trained in a weakly supervised fashion using contrastive loss on massive amounts of image-text pairs in the scale of hundreds of millions of samples. Once trained, such models can be used for identifying any arbitrary concept expressible in natural language given an image. This kind of prediction is known as open vocabulary prediction. A CLIP model has an image encoder and a separate text encoder. For a given image, a vision transformer-based image encoder, produces token-level representations for disjoint patches in an image, as well as an additional token representation called the CLS token for the image as a whole. The CLS token then passes through an image embedder to produce the output from the vision side of the model. A similar process is carried out on the text side with a text encoder and a text embedder. Note that the image and text embeddings are of the same dimensionality and are trained to lie in closed regions of the embedding space for similar concepts. Thus, given an image and a set of classes expressed as text, we can compute the cosine similarity between the image and text embeddings and use them as logits for classification. At this point, a natural question is whether these CLIP models can be leveraged to perform dense prediction like segmentation in an open vocabulary manner as well. There has been some prior work on this front. One of the popular works in this regard trains a separate image encoder to produce pixel-level representations and uses segmentation annotations in a fully supervised manner while keeping the annotations close to the text embeddings using a frozen text encoder. Another work develops a framework of training with a segmentation loss and a region-word grounding loss using not supervised segmentation annotations but class-agnostic segmentation masks to train an open vocabulary segmentation model. Yet another popular work, GroupVit, proposes a modified vision transformer architecture with separate learnable group tokens to encapsulate concepts within regions of an image. This work does not use any segmentation annotations or masks, but changes the architecture of the vision encoder and hence has to be trained from scratch. In this work, we start by exploring if we can leverage a pre-trained CLIP for the task of open vocabulary semantic segmentation. To do that, let's get back to our CLIP architecture from before. Remember that image encoder produces patch tokens in addition to the CLS token? We first ask if the desired alignment between the text and image CLS tokens also extends to the patch token. To do this, we run the same process of classifying each patch tokens as we would a CLS token. We do this on Pascal VOC, where we can label each patch token using a majority vote of the pixel labels. On carrying out this experiment, we find that patch-level alignments between image and text in general don't exist. This is evident from the low pre-alignment patch classification accuracy in this table. Indeed, there is nothing in the CLIP loss that would encourage such a patch-level alignment to form. The next question is then if we can use these patch tokens for any purpose to solve our problem. Do they store any kind of semantically useful information? To study this, we explore if the image encoder of CLIP has semantic coherence. In other words, if semantically similar regions of the image correspond to similar representations in the corresponding patch tokens. Note that this has already been studied in another popular model called Dino, where such semantic coherence has been shown to exist and has been used as a basis to use Dino for unsupervised segmentation. To check for semantic coherence, we use the cosine similarities between patch tokens obtained from within an image as well as across images and use the similarity as a binary classifier to identify if the tokens represent the same concept. Our results are encouraging. As it turns out, we find that CLIP can actually outperform Dino on semantic coherence and hence can indeed leverage the patch tokens from a pre-trained vision encoder of CLIP. Interestingly, we find that CLIP's WIT-B16 has a better performance than CLIP's WIT-L14 on semantic coherence, even though WIT-L14 is a larger model. This finding indicates that we can train a patch-level alignment between the image and text encoders. However, we still need to do it in a weakly supervised fashion. To do this, we define a modified compatibility function for contrastive loss called patch-aligned contrastive learning, or in short, PACL. First, we get the patch tokens from the image encoder and the CLS token from the text encoder. We pass them through their respective image and text embedders and obtain the corresponding embeddings in the joint dimensional space. We compute the cosine similarities between the CLS text embedding and the image patch embeddings and use those as coefficients to form a linear combination or weighted sum of the image patch embeddings. Finally, we use the cosine similarity of this weighted sum and the CLS text embedding as our image text compatibility function. On training just an image embedder on top of a pre-trained frozen CLIP model using PACL, we find that the patch level alignment between image and text significantly improves. This was our desired goal. Thus, with PACL, we can use this model for multiple purposes. We can use the image text compatibility function phi hat as logits for image level predictions like zero-shot image classification, just like we use CLIP's cosine similarity as logits. At the same time, we can use the patch level alignment a x, y to identify regions in an image which correspond to a given class or concept. Naturally, this alignment is useful for zero-shot transfer to open vocabulary semantic segmentation without using any segmentation annotations, with simply training on image text data. We test this on 4 different benchmarks and obtain performance consistently better than previous baselines. One thing worth noting here is during inference, to get more fine-grained predictions, we reduce the stride of the first conv layer of the pre-trained vision transformer. This does not have any impact on the weights, but provides a much larger number of tokens. Performing the same image text alignment on these tokens helps in generating a fine-grained segmentation mask for images. We perform an ablation across training datasets and vision encoder architectures and find that even with Dino, we can attain competitive performance with other baselines. In fact, the order of performance seems to follow the same order as we observed in semantic coherence. Encoders with high semantic coherence achieve higher performance. Thus, PACL is a flexible method which can be applied to different pre-trained vision encoders without requiring any training from scratch. Finally, as we mentioned before, PACL can be used for image-level predictions as well. Across a suite of 12 classification datasets, we broadly find that PACL is competitive or outperforms its corresponding vanilla CLIP counterpart when it comes to zero-shot image classification. Thank you for watching this video, and feel free to send me an email for further questions.